Okay, so here we go. Paired tests in Chapter 25 are generally tests where we pose a treatment on a subject. Well, if you remember, where do we impose a treatment on a subject was in Chapter 13 when we did experimental design. These are generally before and after scenarios involving the same person. For example, we could get a student's SAT math score, send them to an SAT prep course, and then test their math score after completing the course. So, last chapter, we looked at two separate populations. Let's say we're looking at the math for males and females. And there was a mean math score for SATs for males and a standard deviation for males, and a mean math score for females and a standard deviation for females. Okay. And then we took a sample from each of these populations. And we got an X bar and a standard deviation for the sample from both of these. So this would be X bar sub F and S sub F. And then we compared them. And we said, oh, is there a difference in the samples? Is there evidence of a difference in the samples? Because what we're looking to see is, is there evidence that males do better or do worse in math than females do? Okay. So, when we compared them, they were independent of each other. What males do in math is independent of what females do in math. Now, in this situation, in this chapter, we have all these students. And they have a mean SAT math score and a standard deviation for that SAT math score, and that's in the population. So we pull a sample of these students, and we say, oh, okay, let's see how good you are in math. And we give them a test. We call that X bar sub B and S sub B. And that is their score before we do anything. That's why we call it a B. And then we take that same sample. So these are the same people. And we say, oh, okay, let's see how you did. X bar after and S sub after. Now, the problem is we can't compare X bar sub B to X bar sub A. So, these lack independence. So we can't do a two-sample t-test. So we have to say, okay, you're the same people, so we're going to kind of treat this as a one-sample t-test, and here's what we're going to do. We're going to take the results of those two samples, and we're going to say, okay, here's what we're going to do. We're going to see what's X bar sub of A minus B. What's the difference in your average SAT scores? And we're going to say, well, what's the standard deviation of that difference? Okay, and really what a match pair t-test, we're going to kind of treat it in a similar way as a one sample t, in that we're going to take the before and after data, and we're going to create a third list, and that list is going to be called the difference. So this X bar of A minus B is actually going to be X bar sub D, and this S sub A minus B is going to be S sub D. And that's going to be the standard deviation of the difference. And that's really what we're going to wind up testing when we do a match paired test. Okay, so the problem we face is that these lack independence. because the same person is doing both. So you can't say they're independent samples. They're not independent samples. So we all have to do this test differently. We will actually test the differences between the before and after results and see if there is a significant change. This is called a matched paired t-test, or you could call it a paired t-test. Mu is actually the mean difference, so we call it mu sub d. For a hypothesis test, we will always assume that there is no difference. So H sub O will be mu sub d equals 0. The alternative will depend if we want to see the difference increase or decrease. So H sub A can be mu sub d is less than 0. Why would mu sub d be less than 0? Well, very simple. Let's say that you're doing blood pressure. You do an experiment. You test the people's blood pressure, you do a treatment under blood pressure, and then 10 weeks later, you then go and retest their blood pressure. Well, what do you want to see happen to the average blood pressure? You want to see a decrease. So in this case, we would want to see the mean difference be less than 0. We would want to see that it went down. Okay? Or mu sub d could be greater than 0. Okay? So, when would we want to see that? SAT scores. We test people's SATs. We then put them in an SAT prep course, and then we retest them 10 weeks later, and we say, okay, let's see how you do on the SATs after. Well, we'd want to see a mean increase. Okay? Alright, so the conditions for a match pair t-test are similar to all of our t-tests that we've been doing. We have a random or representative data. Okay, we have the less than 10% condition because we're sampling without replacement. Now the third one, because we're dealing with independence, we're dealing with a before and after scenario. We would say, oh well, the samples should be independent. Well, they're not. So you can't say independent samples. So that condition goes out the window. Okay, so we're going to call this the paired data condition. Okay, and then the fourth one is that is what we call the nearly normal condition. In this, your central limit theorem rules apply. You know, if you have a sample that's greater than 40, then you can assume that it's nearly normal by the central limit theorem. Anything between 15 and 40 has to be roughly unimodal and symmetric, and anything that's less than 15 you have to be pretty careful with, watching for outliers and skewness. Okay. All right, so the formula here, remember our formula for a t-test is going to be, since we're dealing with quantitative data, we got to use a t-statistic, right? So this is going to be very similar to a one sample t. You know, remember a one sample t was x bar minus mu divided by s over the square root of n. All right, well, all we're going to do here is we're simply going to do x bar sub d minus mu sub d over s sub d divided by the square root of n. So it's the exact same formula as a one sample t-test. And basically we're going to be testing the differences between the before and the after data. Okay? Confidence interval will be interpreted for the difference in before and after data. So remember, in a one sample t-test, confidence interval was x bar plus or minus t with certain degrees of freedom times s over the square root of n. Well, it's the same deal. X bar sub d plus or minus t degrees of freedom, s sub d over the square root of n. So those are your formulas for the paired t-test, which is the same as the one sample t-test. Alright, so this is example 1. What I would suggest right now is put your data in your calculator in list 1 and list 2, before goes in list 1, after goes in list 2, and then continue. Okay, so one indicator of physical fitness is the resting pulse rate. 10 men volunteered to test an exercise device advertised on television by using it 3 times a week for 20 minutes. The resting pulse rates and beats per minute were measured before the test began and then again after 6 weeks. Results are shown in the table. Okay. So we have basically 2 samples of data. One was collected before and one was collected after. And we have the same 10 people in both samples. So first of all, we have quantitative data. So we know we're dealing with a t-test. And secondly, we have matched samples. You know, we have a before and after, so we have a paired t-test. Okay. So we're going to go through this. So when we're dealing with that, our parameter is now going to be mu sub d. We're not going to do mu sub b and mu sub a because they're not independent. And that is going to be the mean difference in resting pulse rate after using device for 6 weeks. Our hypothesis, our assumption is, this is H sub O, is that the difference does not change. Now what do we want to see happen to pulse rate if it's effective? Well, they gave us the answer right here. We want to see if it reduces pulse rate. So the alternative is going to be that mu sub d is less than 0. Our assumptions and conditions. Okay, these 10 men volunteered, so we're going to say that this is the sample is representative. Uh, 10 men is less than 10% of all men. I guess we're looking at adult males. We'll say adult males. We're not going to say that samples are independent. We're going to say that samples are paired by before and after. Okay. And then we got to get into this nearly normal condition. We only have 10, so we got to check this. All right, so it's in your calculator. Now, here's what we're always going to do. In L3 here, you got to go to the top. Don't put it in the first row. Go to the top, and you do. You're going to, if you want to see if pulse rate went down, you would have to do the after minus the before. Okay. So that would be the change that you'd want to see. So you're going to do, and you're always going to do this in a paired data. You're always going to do the after, which is L2 minus L1. And there you go. Okay, so that's the list we're going to be dealing with. Okay, that's the list of the differences. So you see what happened. One person didn't change, a bunch of people went down. One person went up. So out of them, one person didn't change, 8 people went down, 1 person went up. Okay, the pulse rate went up. Alright, so now we got to go to stat plot, and we're going to put plot on, and good. We're going to test list 3. Okay, make sure it's on histogram, and then do zoom 9. And that looks pretty good. Okay, you might argue it's a little skewed right. That's okay. It's roughly unimodal and symmetric. So our window starts at -8 and goes to 3.25. Okay. So So it goes like this. We're going to put this on our paper. And this is -8. This is 3.25. So we're going to say that the data is roughly unimodal and symmetric. Okay, so we're going to name the test. You could call this a paired t-test or a matched paired t-test. If you put down 2-sample t-test, it's wrong. You cannot put down it's a 2-sample t-test. You cannot put down it's a 1-sample t-test either. It's a paired t-test because there are 2 samples presented, before and after, and we're testing the differences. Okay, so here's what we're going to do next. We got to get our statistics. So you're going to go to Stat Calc, one var stats, and your list is going to now be L3. So we got to test L3. So X bar is -2.8. The standard, and I'm going to call that X bar sub D. The standard deviation of the difference is 2.53. N is 10. Degrees of freedom then will be 9. We don't have to worry about that complex formula from chapter 24. Simply we treat it as a 1-sample t from here. Okay. Now we obtain P. So T equals X bar minus mu, well, we're hypothesizing that mu is 0, divided by S, 2.53, divided by the square root of n. Okay? And at this point, we're treating it as a 1-sample t-test. So we just go to stat t-test, and we say, okay, we're going to do it from the data. And our mu, our hypothesized mu is 0. And our list is L3. And we're doing less than, because that's what our alternative hypothesis is. So this always matches this. Okay. And then we're going to say, okay, calc, go ahead and draw that up. And of course we have our stat plot on, so that's why those lines are behind it. If you turn your stat plot off, that's good. Those lines won't come up, but I'm just going to ignore them because I don't really need them. I just need the graph. So here we go. So our t-value is -3.5, and we're shading in way over here. And our big p-value is 0.0034. And let's say we're testing at the alpha is 0.05 level. So make a decision. We reject H of O at the 0.05 level. And our conclusion is there is strong evidence that the device, when used as described, will reduce the average pulse rate of adult males. Okay. So, approximately how much should a person expect the program to affect resting pulse rates? So, if we wanted to try to pin down a value, we would have to do a confidence interval. So we did a, they should have told us what confidence interval to do. We did a one-tail test at 0.05, so we'll do a 90% confidence interval. Okay, so we're going to go, again, it's just confidence interval equals X bar plus or minus, we got to figure out that t value, times S for the square root of n. Now, again, we're going to do the same thing we've been doing, 90% confidence. We do the middle 90%. Where does that start? That starts at the 5th percentile and ends at the 95th percentile. So we're going to go and get that t value since we only have 9 degrees of freedom. So do second distribution. And we say, okay, inverse t, and we're going to do 0.95 or 0.05, whichever one you want to do, and our degrees of freedom here is 9, and that comes out to 1.833. Okay, so I'm just going to put that in here. And at that point, again, we're doing this the same way we would do one sample t-test, the mechanics of it. So I'm just going to go into stat test, and I got to find t-int. There it is. And already I'm on data, and I'm going to do L3, and this is a 90% confidence interval, and I'm just going to calculate the interval. And it comes out to negative 4.3 to like negative 1.3. Okay, I'm truncating it, but so our interval came out to negative 4.3 to negative 1.3. So we are 90% confident that the exercise program described above will reduce the average or the mean pulse rate of adult males by between 1.3 and 4.3 beats per minute, right? Yeah, beats per minute. Okay, and there it is. We're all done with the match paired t-test.